All right, folks. So welcome to our third lab class. Okay. So today I want to go over the sample problems that I introduced last week. And then what we'll also do is we'll look at your actual thing that's due, the thing you need to submit, which is this exercise, rendering the line. Okay. So what I'm expecting you guys to have by the 21st, so that's in 3 days, um, is this line drawing from a starting position given an angle and a launch speed. Okay, so that's what I want us to do. If you want help finishing that, then we can do that. Um, if we finish class in time. So let's go for it. Uh, how many of you guys had a look at the sample problems?
I do, and right now I'm already doing one of the practices on the
Doing one of them.
notes.
Very nice. Very nice. So I'm gonna go over solutions, but I do appreciate that you've gone ahead and worked on it. Right, that's really good. Um, so last week we talked about this set of equations here that is the kinematic equations, but just applied in code. So the kinematic equation defines motion when given an initial position, a initial velocity, a constant level of acceleration, that is gravity, uh, and a time value. Then we can get a new position out. And this is just going to allow us to do that, but over this a set of a few frames where our time value is not absolute time since the beginning of the game, but instead our time value is delta time. So it's dt. In this case, dt here is representing delta time. Each one of these is a single variable. Um, it's not a times y, it's just ay because this is code. Okay, because we're making this discrete simulation of little steps of time. So one of the sample problems was Mario has this velocity in x and y. So the question is, what is their speed? Could any of you answer what the speed is? What is Mario's speed? 1a. What did we get for 1a? What is his speed? If you didn't do it before, you can quickly do it right now. It's a very quick problem to solve. All right, here's how I expect us to solve it. You have a velocity of 4 on x and negative 3 on y. So let's draw a picture. You create a graph, okay? You have an origin, uh, 1, 2, 3, 4 on x. That's 4. And then let's do green for y. 1, 2, 3, 4, 1, 2, 3, 4. This is about negative 3. All right. So here is our uh, y of -3, and here's our x of 4. Okay? So what do we have here? Well, we have a vector, yes, but that vector happens to be a right angle triangle. Right? So this is a right angle triangle, and we know the lengths of two of the sides. As it happens, we know the length of the two sides that are the shortest, not the longest side. So let's look at that, right? You could make a triangle. You could make this these three sides, and then you have something where this is A, this is B, and this is C. So how would you do that? You'd think of this. You think of Pythagorean theorem. You apply that by saying the side length of x, this horizontal portion, squared, plus the side length of y squared is going to be equal to the side length of this hypotenuse. We'll just call it h squared. Okay? So if you take the square root of all of this, then you have, and you just put it the other way around, you have h equals the square root of x squared plus y squared. What's x squared? 16. 16. What's y squared? That's 9. So that will add to 25. Okay, so h equals the square root of 25, which is 5. So that right there, that's 5. That is Mario's speed. See, he has a velocity that is these two pieces combined in x and y, and the absolute magnitude of that vector, you could say it's the magnitude of the vector we're taking, right? The magnitude of that vector is 5. So the length of that vector without caring about direction is 5. Velocity is a vector. It has direction and a magnitude. Speed, we're just looking for the magnitude. So the answer is 5. Great. So, B. Did we try B? Okay, so here's our solution for A. Great. Let's try B. So for B, again, I recommend you draw a picture. This is going to involve triangles as well, but yes, you should draw a picture. So you come up with something, 8, 6, somewhere like here, sure. And there's a Goomba at 0, 1. So 0, 1. Okay, so there's a Goomba. Okay, and there's Mario. Okay, I'm just drawing the hat. What angle does the Goomba have to look up at from the horizontal? So you know that the Goomba is looking up at Mario, and there's some angle here from horizontal. And that's what we want to know. All right, let's just call that alpha. So it's A for angle, alpha. Okay, so what angle does the Goomba have to look up from its horizontal? Part of the key here is we have two steps. First of all, we have to make a triangle. Then we can figure out the angle of that side from that triangle. So how do we get this triangle? We have a triangle here where this is a right angle, that's 90 degrees because x and y are orthogonal, okay? And then this right here is the angle we care about. So what do we have here? How do we get this triangle? Well, we have these two positions. We can get a vector between them, right? So we can get this vector right here. So what is the vector at which the Goomba has to look up at to Mario. If we were to subtract their positions, we would get what the difference in position between them, right? So we would be able to get Mario's position and subtract Goomba's position. So 8, 6 minus 0, 1. You could just kind of do that, and then what do you get? 7, 5. So what's 7, 5? That would be the side lengths of these triangles. So that means this is 7 horizontal. Sorry, why did I write it that way? 8. I don't know why I wrote that. So this is 8, and this is 5. Okay? The difference in x position is 8. The difference in y position is 5. So now you have a triangle where you have two sides. And since you have two sides, you actually also have the third side. So you have all three side lengths of the triangle. Okay? And you have this one angle. You know it's a right angle triangle. So using that, you will be able to figure out this angle. Okay? It's getting a little messy here. But what do we know? What sinusoidal function do we know that relates side lengths to an angle here? Let's say with these two side lengths, relate these two side lengths to this angle. Which function relates those three things? I could rephrase it. This is the opposite side. This is the adjacent side. Adjacent to the angle. And this is opposite to that angle. And this long side here would be the hypotenuse. But we don't really need that. We can get it, but we don't really need it if we have these two already. So there's a function that has opposite and adjacent, and that is tan. That's right. That's why we have SOHCAHTOA. TOA is what we're looking for. The tangent of this angle, tan of A here, would be equal to the ratio of opposite over adjacent. Okay? So we know that this is true, but we need to somehow manage to rearrange it to instead say alpha equals something, something, something. So what do we need to do to get that done? The problem here is we don't have alpha sitting out on its own. Right? So we need to do something to find a way to rearrange this equation or something, right? To get alpha out of here, out of being inside the tan function, and just have it sitting on its own so we can solve for it. We need to solve for alpha. So we could take the inverse function. Yes, whatever we're going to do with an equation, we're going to do it on both sides. So here's what we're going to do. We're going to do tan inverse. And then what we're going to do is we're going to end up alpha equals tan inverse of 5 over 8. Okay. We invert this. The inverse function of tan is going to take in this output and then give us that alpha. It's going to go the other way around. It's a reverse machine. Pretty sweet. Okay, so how does it look? Let me erase a little. Here we go. The tangent of this angle is going to be this over this. So the tangent inverse of this over this is going to give us our answer. And then all we would need to do is plug in the numbers. We would say they're different by 8 horizontally. Oh, sorry. That one's horizontally. Different by 8 horizontally, and different by 5 vertically. And that's it. Very nice. Cool. Let me see. What was the last one here? Oh, this one is more complicated. Okay, this one is more complicated. Did anyone complete this one? This one requires you to use the quadratic equation. Um, and there is another tricky part, but yeah, we'll see. There's a tricky part, but uh, there is a quadratic formula which is just this the quadratic equation but rearranged. That solves for the variable. And in our case, it's going to be solving for t. Okay, the quadratic equation is the whole like the negative uh, b plus or minus the square root of b squared minus 4ac over 2a. That thing. Okay, so let's look at this. So first of all, we have to recognize all of this stuff and plug it into the kinematic equation. So we have to arrange it to fit the kinematic equation. The kinematic equation goes like this. Okay, so we have a final position, we have an initial position, we have an initial velocity, we have time, and then we have half at squared. So the motion of something, it actually uses half the acceleration value. You can think about it as actually being the average acceleration over this period of time. Okay, so this is probably why you guys have some potentially different numbers, but we'll see. So half at squared is what we use for kinematic equation, where a is our acceleration parameter, and that's the one that goes next to t squared. So if you know your quadratic equation, it goes like ax squared plus bx plus c, right? The kinematic equation is, well, it's this, right? Where that maps to that, half a is a. Half a in the kinematic equation is a in the quadratic equation. Okay, vt is that, so v is b. Okay, and well, we do equals 0, but or equals y, right? But so we could say y equals that, and then this is c. Okay. So using the quadratic formula, we have to make it equal 0. We do have Mario trying to land on a platform at y equals 1. So what all we are going to do is say that d1, our final position, is going to be 1. Okay, but then we're just going to need to subtract it from both sides. So we'll just subtract it from both sides, and then we'll just end up making that into 5. That's 6 into 5. That's all. Because the question is, Mario's at 8, 6, and the platform is at y equals 1. So all we're really asking is how long will it take for him to fall 5 units, right? He's falling 5, he's not falling 6. So that's how this works out nicely. So we're just asking, he's going to move 5 units. We're simplifying it. Okay, so we plug in our velocity. Our initial velocity was -3 on y. Okay, so we plugged in our initial velocity here. And then our acceleration value was -2 units a second squared. So we plug -2 units a second squared, but we have it because the kinematic equation halves our acceleration value. We have to do half acceleration. Okay, so that's what we actually end up putting right next to times squared. Okay, so we plug that into the quadratic formula. Remember, this is A, this is B, and this is C. It's kind of backwards. So we have this, negative, or negative B, okay, -3. That's just 3. Plus or minus the square root of B squared, -3 squared, minus 4AC, 4, A is -1, and C is 5 over 2 -1. And that simplifies pretty nicely. Okay, we'll end up with 3 plus or minus the square root of, let's say, 9 minus 20, minus 4 times -1 is -20. Okay, so it's plus 20. Over -2. And this is plus or minus. Anyway, what we really cared about, though, is just writing the equation so we can plug it into a calculator or write some code for it. So we don't really need to worry even about the numbers. We don't really care about the numbers. We can use the numbers to kind of verify if what we did made sense. But as long as we put the right numbers in the right spot, as long as we did the equation correctly, then we're fine, right? So in code, we're just going to make variables for all this, and we just need to make sure that things are actually multiplying where they're supposed to. That's all. How much time we have? Oh, we've almost used a whole hour. Okay, I'll try and speed up. I will speed up. Okay, this one is very relevant, though. I should not speed up for that one in particular. This one is really relevant to what you are doing right now with that lab exercise. So if you have a given launch angle, a given speed, then what is the x and the y of that velocity? So Slingshot says we are launching a bird with 100 units a second at 30 degrees, then this does create a triangle. This does create something where we could calculate what is that vector in terms of x and y. So we want to figure that one out. That's what we want to do. Okay, so how do we do that? We just use sine and cos. We have an angle. We have a third side. We need to use that to relate this side length or this side length. So we will need actually two equations. The sine of this angle is going to be opposite over hypotenuse. Opposite y over 100. Okay, so if the sine of 30 is equal to y over 100, then what is y? How would we solve for y? All we would need to do is multiply both sides by 100 here. So you just say 100 times sine 30 is equal to y. Easy. Or y equals that. Okay, and you do the same thing for x, because cos 30 is going to be x over 100. More generally speaking, it's 100 is our speed variable, right? That's speed. So whatever speed you set, that's what's going to go there, right? So, and whatever angle you set, that's what's going to go here. So let's just say angle is b, angle is b, and then we have speed. You just write a line of code that looks like this, and a line of code that looks like this. Well, kind of like this, really. Y equals speed times sine b, x equals speed times cos b. So all you need to do is create a vector made out of those two pieces. How might that look in code? Let's actually do that. So let's go over here. We have a line drawing function. Right now I'm drawing circles. I don't need the circles. I'm going to hide those circles. Bye-bye, circles. Okay. Draw a line. There's a bunch of them, but draw a line. Start position, end position, thickness, and color. Ah, that's a good one. Yeah. So let's say our start position. Let's make up a start position. There is a vector 2 class. I believe it's just 2 floats, so I should be able to say my start position is going to be screen 10 and screen height minus 10. Yeah. Pixels, in pixels. Cool. Then I have a velocity vector. For now, let me just set it to something static, and then we'll draw ourself a line. Start, pause, and let's say start, pause, plus velocity. This is asking for a starting position and an ending position. Let's draw it in red. So keep in mind, this is asking for a starting position and an ending position. So if you want to draw a line, and you're supposed to pinpoint a starting position and an end position, and what you have is a starting position and you have a vector, then how do you find that end position? You take that starting position, add that vector, then you have your ending position. You don't just put velocity here as your second part, because that's not a position. Okay? I can show what it looks like if we do it wrong as well. Let's see what we get here. Oh, okay, I do see a red line. It's going the wrong way. I think I would like to invert it. Let's invert it. Negative 100. Okay, so there's a little line. Great. Now what would happen, let's say what would happen if I just put velocity as the second component here. What would happen? This is what I would get. I'd get something a little goofy. Okay, so, alright, let's determine velocity correctly. Okay, I'm going to make a variable for speed. I'm not going to make a variable for everything else right now. I'm just going to make one for speed. Alright, and we can make a slider for it as well, using this GUI slider thing that we used for time. Oh, you're having trouble seeing the code? Even at this zoom level, huh? Okay, hang on a sec. Zoom. What have you done this time? We pay a premium for this. Video settings. Do you think it's too small, or is it the the image quality is bad? Quality is low. Okay. Darn Zoom. All right, let's try this something here. HD video. Yes. Uh. Hmm. Is this any better? Come on, Zoom. Same as before. Come on, Zoom. Please. I'm not even recording or streaming to multiple places at once. Hmm. Not recording to a cloud, I mean. Maybe I can zoom on the code. What? Oh, yeah, I can do that, but it should be legible. I think at this like scaling, I don't know why it would give such trouble at this kind of scaling. Um, Settings video. Yeah, enable HD. Hmm. Video statistics. Oh yeah, the resolution is really poor. It's 640 by 360, but that is not my streaming resolution. That's awful. Uh, yeah, the HD button is on, but it hasn't been changed. Yeah, it's a good thing the college wants us to use Zoom, isn't it? The college is quite generous. Uh, yeah, guys, I don't know. I think if I do screen share, it might be better though. So let's try that. My fancy streaming setup won't work at the same time, but let's try this. Better, at least for now. Is this better for now? Okay. Yeah, I don't know. It might be a limitation of Zoom's, video quality thing, uh, for my virtual webcam. Yeah, I'm not sure why they have it like that. Okay. Well, we'll see. Okay. Cool. All right. So here's what I wanted to do. I wanted to make another slider bar. So here's what I'm gonna do. I'm just gonna copy paste this one that we had for time. I'm gonna make one for not time. Uh, let's see, X, Y. Let's set it to 40. The width doesn't need to be so long. this is not going to control time, instead it's going to control speed. And I don't need it to do decimal places. You know what? I'll keep it whole as well. Yeah. Okay, so speed is going to be a float, but I'm not going to handle it with any precision here. And the min and max value. Okay, so let's do a min value of negative 100, and we'll do a max value of 1,000. Alright, let's see what I get. Oh, with the slider. If I can play with the slider, then we'll be able to stick speed in there somewhere. Don't worry about this other line. Okay, slider seems okay. Alright, so now we have a slider for the speed value. Let's stick that into our velocity. Here's what you shouldn't do. Don't do just something like that. That will look okay, but it won't actually be okay at all. Like, at all. It will not, it is not okay. Here, the thing is, computer will let you do whatever you want, but there's only one actually correct answer. It's not going to tell you by having a compiler error if you put the numbers in the wrong places, because the computer doesn't know that you're dealing with speeds and angles or something like that. It just knows you are trying to feed it numbers. So let's say I give it an angle, 30, okay. If I put angle in here, it's not going to stop me, but it is absolutely incorrect. There's no reason to put angle here as the x component of a velocity, right? But it's not going to stop me. There's not going to be a red squiggly. So remember, just because there isn't a red squiggly, just because it isn't throwing an error at you, doesn't mean you've done it right. You know you've done it right when you've done the math right, okay? When you've actually done the math right. That's really what we're looking for. Okay, so let's try and apply that thing we learned with sine and cos. Okay, so what did we use for x? We used so and cap. And when we have this triangle, that y is opposite. And the x is adjacent. So when we're doing x, we're going to use cosine. When we're doing y, we're going to do sine. Oh, that works nicely. Cos angle. We'll keep it negated when we do our y. Yeah. Sine of angle. Okay. And we're going to multiply these both by speed. Okay. Let's see here. Something seems off. Definitely something seems off. What's still wrong? There's something still incorrect. Nope, it's not that. It isn't that. No, right now, that's not actually the most problematic issue. The most problematic issue is this right here. How we need to draw our vector. Because we're supposed to give an end position, not just a velocity. Oh, but that doesn't mean we'll be solved all our problems. We do have another problem. So this is not the 30 degrees that I expect. That's for sure. Who knows what it is, but it's not correct. We might have an easier time if we put our starting position closer to the middle of the screen. So let's give it at least a little bit more room. 200 pixels in. Okay, and how could we mess with that? Let's try adding another slider for angle. Angle slider. Angle. And instead of negative 100 to whatever, let's do negative 90 to 90. So we'll have 180 degrees. No, let's do negative 90 to... Let's do negative 180 to 180. Okay. We'll keep that where it is. We'll just move it slightly further down. Okay, so... Maybe I'll make these sliders a little longer. Okay, so now we have another slider for angle. So that one is angle. There's something wrong here. There's definitely something wrong here. So when it's set to 0, 0 looks fine. But then I go to 2, and it's way off. We did have a hint earlier as to... somebody gave a hint as to what's wrong. But anyone want to hazard a guess at what is wrong here? Let's look at the code. Clearly, this second slider is not representing angle the way we're expecting it to. Let's run it again with labels on these. So what's going on? Ideas, anyone? Any ideas? Coordinates? Am I adjusting the angle? Yes, I am. I am adjusting the angle. Here, I'll make it bigger so you can see more. Okay, I'm gonna make these sliders really big. Okay. Oh, the font size isn't that big. Huh. Yeah, you can't really see the font size too much. That says angle 30. Either way, does that look like 30 degrees to you? No. Let me set it to angle 0. Angle 0, that's 0. That's correct. Make angle negative angle? Well, let's say this is angle 4. That's 4. Anyone else have an idea? So let's look at all the things affecting this velocity. Okay, so there's the drawing. All right. So if we did the drawing correctly, then there's these two components. Start pause. Start pause is fine. Velocity, maybe there's something wrong with that. Is speed too high? No. Speed being too high would affect them both the same because it's multiplying both sides by the same value. Is it the cos and sine of these angles? Why would it be wrong? Let's look at the documentation for cos. So this is in math.h. That means this is using just regular like C math library, the C standard math library. Okay, so let's look up the C Standard Math Library. C Standard Math Library. CMath, math.h. Okay. Functions, cos and sine. Okay, let's see this. Cos returns the cosine of an angle of x in radians. So parameters, this is inputs, things that go in. 1 radian is equivalent to 180 over pi degrees. So here's an example. If they want, it says the cosine of param degrees is so on. And what did they do? They took 60 degrees and they multiplied it by pi over 180 before sticking it into cos. Because cosine function here, cos, takes radians. So if we want to give it degrees, we need to convert those degrees into radians first. All right, so we could go and do that pi over 180 stuff. So you could do that. I think there is a constant already that we have access to called deg2rad, which happens to be equal to pi over 180. So here they multiplied it by pi over 180 to get it done, because 1 radian is 180 over pi degrees. Okay, here's what we could do. We just define that as a constant, pi over 180, and then just multiply it by that constant. Same thing is available in Unity. Okay, great. Let's do this. Angle of 30 is good. Okay, so this is 0. This is 2. This is 16. Here, let me increase the length of this vector, and it's more obvious. That's 90 degrees. Do you have to use sliders? You can use anything as long as you can actually change it, but I recommend sliders. There are other GUI elements that are available to you using this framework, but you need to have a way to change these numbers in real time. Let me check the assignment sheet to see if you can do it with arrow keys. I'm probably okay with it, but you need to have instructions on screen to say how to do it. Yeah, you'll need to put instructions on screen. Yeah, allow them to be adjusted individually. Yeah, it's fine then. Yeah, that's fine. We also need something for position. So arrow keys can be done with position as well. I didn't do that here yet, but I'm sure you guys can figure that one out. Okay, something that's important is that we shouldn't see the length of this vector changing based on the direction. Let's see, does it change based on the direction? Nope, it looks like it's tracing out a circle. That's good. Is that a circle? Yeah, it looks good. Okay, so this is almost everything that you would want for that lab exercise. You'd also want to be able to change the starting position in real time. But that's about it. So this plus changing the starting position. That's all you need. Cool. All right, but let's go a little further with some of these sample problems. If you want to launch yourself a bird, you actually want it to move across the screen. That's going to be our next step, right? Our next lab exercise is going to be actually launching the bird. where we're going to have multiple objects and we want to contain data for these things, and then we want to actually be able to shoot them across the screen. Okay, so all of this stuff, to do that, we are going to need to understand the mechanics here first. So let's write a set of equations that we can turn into code easily that model the motion of a bird in 2D when launched with a constant acceleration due to gravity, no air resistance, and a certain starting position, and a certain starting velocity. Like we did before with the speed and b representing our angle. When I'll get back to you when Connor reminds us what the plan is there. I think you are expected to do both. It might be that you're expected to do both. Yeah. Let's see. Every exercise is going to be a video. You must have a video explanation. Absolutely. Okay, so let's look at this. Here's our kinematic equation, right? Our final, we're going to split it into two parts, x and y. The x component is really easy because we do not have acceleration in the x direction. This is what we like to do in physics. We like to split things up into components. So we like to say, all right, there's this whole motion, but we're going to say split this motion up into two parts. There's the up and down, right? And then there's the horizontal. Okay, and that makes it a lot easier. All right, horizontal is just our x. So instead of thinking about this in 2 dimensions, we think about it twice in 1 dimension each. It's a lot easier. Break it down. Okay, so the x direction, what's the x direction look like here? So we're launched from the sky. We have no acceleration in the x direction, because acceleration due to gravity only applies up and down. Okay, that's our gravity. So in the x direction, it doesn't even matter. We have no acceleration in the x direction. So let's plug in our kinematic equation. Our position in x is going to be equal to our original position in x plus a constant velocity in x times time plus acceleration in x, which is 0, times time. So we may as well get rid of that. Okay, and let's say we can simplify this further and say our initial position in x was 0. We started at 0, too. So 0 plus, what was our initial velocity in x? Our initial velocity in x was this. We figured this out. That's vx. Speed times co-speed. All right, and then there's time. And then our acceleration in x was 0. So the only thing that matters is actually this. Like, this is the whole thing that matters. The others we can ignore. Right? Cool. So now, to model the motion in the y direction, what are we going to do? We're going to say he starts at position 2. Okay, so that's 2. 2. He has an initial velocity in the y direction equal to something we worked out before, speed times sine of the angle. Okay, and then multiply that by time. Okay, and the acceleration value, we're going to have to half that. So whatever gravity is, we're going to have it for this. So if gravity is 9.8 meters per second squared down, then this is going to be 9.8 divided by 2. It's going to be like 4. It's not 4.5. 4.9. 4.9. So this is gonna end up being about 4.9 ish, right? If gravity is 9.8, this just be half gravity. Okay, cool. So that set of equations is basically, this is what we're going to use to actually model that motion. All right. If there is a floor at y equals 0, we can predict where the bird will touch the floor using the quadratic equation. That will solve our time. We can solve for time, and then we can solve for distance by multiplying our horizontal speed by time. So we kind of did this already with the time Mario is going to touch the ground. You do the same thing, but then if you want to know where horizontally we're going to be, we can multiply that time, the duration that we were in the air, multiply that by our constant velocity in the x direction. That's speed times cos b. And then we would say, we know that the y position is 0, and the x position is going to be that. Well, you know, if you already solved for time, then all of this is just the solving for time. Literally all of this is just time. It's just this stuffed into there, right? It's time. Okay. 30 degrees versus 60 degrees. Interestingly enough, these are really interesting because an angle of 30 degrees and an angle of 60 degrees, they look like they would produce different stuff, but they will actually impact the ground at the same point. That's interesting. Any kind of ballistics problem like this, like you'll have a high angle and a low angle, where both will actually intercept at the same point. And it's based on essentially complementary angles. 30 degrees has the same proportions as a 60 degrees. Just swapped. It's just the x and y are swapped. They have the same proportions. These triangles are similar. If you think about it, this 30-degree triangle is the same as the 60-degree triangles, but this other angle here is the 60. Because all the angles add up to 180 degrees, you can actually figure that out, right? So they are the same triangle, just their x and y are swapped. So that's pretty interesting. Let's not waste too much time here. Okay, cool. So this is the kind of thinking that we're going to need to solve our problems here. Let's look at our next lab exercise. That's this guy right here, launching a bird. So we will need something to describe physics body objects. We will need some kind of simulation to move them across the screen. We will need a container of these. We will need some kind of acceleration due to gravity, and we will need to get control to start this motion. Okay, let's do part of it. I'm going to do part of this. I'm going to get rid of some of these variables. We don't need some of these anymore. I'm going to get rid of those. I'm going to get rid of that. I don't need to draw circles anymore. Yeah. Let me go into the repo and should commit. That I have a partial solution to lab exercise 1. I'm going to commit that. Great. Now I can keep working. Okay, so let's say we have all this start position and things like that. So far, everything's just sitting here in global space. I could also make our a position vector 2 position, vector 2 velocity, vector 2 gravity, acceleration. Let's set that to 100. Oops. Capital V. Capital V. There we go. So let's set that to 100 on Y and 0 on X. Okay. Cool. Let's get some player input here. Now we do have some functions for like key pressed, is key down, some of this stuff from Raylib. Let's say is key pressed. If is key pressed, key space, then we're gonna do something. Okay, I can say we'll set a velocity. So we had this calculation of velocity going on over here. I'm actually gonna take this stuff here. I'm gonna put it in update. And it's only gonna happen when you press space. Yeah. It's gonna happen when you press space. What's gonna happen is I'm gonna set position to that. I'm not gonna be generating start position. I'm gonna be setting position to that. Okay, and then I'll be setting velocity. Actually, I'm gonna use both. Yeah, I'm gonna use both. Hang on. I'm gonna use both. I'm gonna have it in both places. So when I do press space, I'm gonna say position equals I can't do that. Okay. This is an int, so I'm just gonna convert that to float. Okay, and then velocity, I'm gonna assign it this cosine value and stuff like that. It's gonna give me a double. I want to convert it to float. It's fine. Same with this. It's fine. Cool. Cool. And I will draw a ball based on this position value, and I'm going to update the position of this ball based on this velocity value. So let's do every frame position equals position plus velocity times delta time. Does that look familiar? It's just going to do it with x and with y. You could also write this as position plus equals. Cool. And I'm going to draw a circle at whatever that position is. Let's do draw circle uh, position dot x, position dot y, and some radius 100 and red. Okay. So with this, we should be able to launch a ball. We won't have gravity, but let's see something going on here. So if I press space, it's going to launch this ball along that vector, mind you. Right? They use the same math to generate that velocity vector, right? So that is launching this ball with a constant velocity. Cool, cool. I'm going to adjust the parameters here a little bit. I'm going to change the radius of that. Let's make the radius of the circle much smaller. 15 pixels radius. So it's 30 pixels across in diameter. I think that's reasonable. Okay, so we'll do that. Let's also add gravity here. So what does gravity do? Position is affected by velocity. So velocity changes position over time. Position equals or displacement is equal to velocity times time. If we recall, velocity is equal to displacement over time. Right? If velocity is equal to displacement over time, then if you just rearrange this equation, then displacement is equal to velocity times time. That's change in position. Displacement is change in position. Okay? Acceleration is a rate of change of velocity. So you could say that acceleration is delta v over time. So delta v, which would be change in velocity, is equal to acceleration times time. Where delta v is a change in velocity. Okay, so all we have to do is velocity plus equals acceleration due to gravity times delta time. Every frame. I'm doing this in an update function here. So velocity is constantly changing. All right, let's try it now. Wow, that's pretty good already. There you have it. We're launching a ball. Now all we need to do is make this so it's not the same ball every time. Make it so that we can create multiple of them and launch them all. That is another step that we're going to have to do. Okay, I'm going to adjust some of the sizes of these things. Kind of crazy. Okay, and we might want to add more slider bars for other stuff. Might be fun to add a slider bar for gravity. Between negative 300 and 300, let's say. Or no, let's go crazier than that. Negative 600 and 600. Yeah, why not? Let's adjust only the y of gravity's acceleration. So, dot y dot y. So we're only going to affect y. So now I can make gravity more aggressive or less. Or even reverse it. So now gravity pulls things upwards instead. Cool. So that's it for now. This is not a complete solution to that lab exercise. It is asking you to use object-oriented programming, essentially, to create some kind of thing that allows you to have multiple physics bodies. So maybe make a class for this. The class could hold these data instead of it just living in global space. It might be easier to think about that way too. So instead of just having these here, you have something where you have an object, like object A dot velocity plus equals gravity. Object A dot position plus equals so on. All right. That's it for now. Any questions? We can break to more open time where you guys can show me your stuff if you like. Okay, I can stop our recording here. I'm recording locally. I'll upload it to YouTube at some point in the future.
Okay,
Okay.
for the coding, yeah. Yeah, I already done the first practice
All right.
one, so I already finished practice one. If you're wondering,
Good.
the math one I just took it all out of notes. I made it all full.
Good. And do play around with it. Do have fun with this stuff.
Yes,
Okay.
sir.
I'm gonna stop the recording. If you guys want, we can go to breakout rooms. But thank you guys. I'll see you around.
Okay. See ya.